Tell me quickly. Yeah, Anushka.
So basically the cells, like there's electrochemical cells and electrolytic cells.
Okay. Donna, would you like to try?
The study of production of electricity.
Yeah, not only production, but actually there are other reactions which require electricity to be passed to carry them out. Okay.
Yes, sir.
So electrochemistry, we are going to give you, we are going to write the general definition. Anushka, it is the branch of chemistry it deals with the interconversion of chemical energy into electrical energy, chemical energy into electrical, and electrical into chemical, right? It deals with the interconversion of chemical energy and electrical energy. Okay. So cell. There are two types of cell. So what do you understand by Arshan, electrolytic and electrochemical cell?
So in electrochemical, there are solutions involved, and in electrolytic ions are involved.
Yeah. So this, we are going to study it in two parts. Okay. Yeah, Arshan, would you like to try? Donna, would you like to try?
I'm not sure, sir.
Yeah. Okay. So very simple, Arshan.
Sir,
Yeah.
the definition of electrochemistry, the final sentence, chemical energy and
Electrochemistry. Yeah. Just a second. Interconversion of chemical energy actually into. Actually, there is actually the interruption due to some screen sharing was net connection. So interconversion of chemical energy into electrical energy. And vice versa. Okay, is it clear?
yes.
Chemical energy into electrical energy and electrical energy into chemical energy. Right?
Yes.
Person, Dona, I hope it is clear. Right? Okay, so there are two types of cell. Cell is a compartment where we do the chemical reaction. So one is electrochemical cell, another is electrolytic cell. Okay. Electrochemical cell is the cell where you do the spontaneous reaction. What do you understand by spontaneous reactions? Yeah, the reactions which can happen on their own. Okay, which have a tendency to happen on their own. Arshan, is it clear? Dona?
Yes, sir. Clear.
Yes, sir.
Yeah. So spontaneous reactions are carried out. So spontaneous reaction that gives free energy change is negative. Okay. So these are those reactions which can occur on their own. Once started, they can progress, keep on progressing. Okay. So chemical reactions are carried out. Okay. Spontaneous chemical reactions are carried out, and because the reactions are happening on their own, you are using these reactions to get the electrical energy to make a cell. Okay. And okay, the cells which we use, that is actually the electrochemical cell. Okay. In our daily and day-to-day life, normally the cells which we use, that is electrochemical. And what's the other name of electrochemical cell? Anushka, Dona, Arshin, tell me.
So galvanic cell.
Yeah, galvanic cell and voltaic cell. Is it clear? So we produce electricity with the help of electrochemical cell, right? Which has other name galvanic or voltaic cell. And what do you understand by electrolytic cell? Yeah. Non-spontaneous reactions. Okay. The reactions which have positive delta G gives the energy change, they can't happen on their own. Okay. So if you want them to happen, you need to give them energy, and you provide that energy in the form of electricity. Is it clear? So non-spontaneous reactions are carried out by passing electric current. Okay. So this is a basic difference. So electrochemistry includes the study of both electrolytic and electrochemical cell. Electrochemical cell is used to generate electricity, while electrolytic cell consumes electricity and it gives certain compounds which are not found in nature. Okay. So can you give me some example of electrolytic cell, some chemicals which are generated in the electrolytic cell? Any example which you know, any chemical reaction? Yeah, tell me. So NaCl and water, if you put, right, is it going to give you NaOH? Yeah, Arshan, tell me. Is it going to give you NaOH?
Yes, sir.
No, because we put NaCl on day-to-day basis. We don't see NaOH and hydrogen and chlorine gas forming. Okay, all of these are very hazardous substances. We put on day-to-day basis, we put NaCl in water, but we don't see this happening. So this is a non-spontaneous reaction, means it cannot happen on its own. Okay, so what we need to do, but this can happen if you pass electric current. Okay. So when you pass electric current, it can happen, and it can give you NaOH, H2 and Cl2. So this is reaction is carried out in electrolytic cell. This is electrolysis. So electrolysis is breaking down of a chemical substance with the help of electric current. Okay. On the other hand, electrochemical cell is used to produce electric current. Okay, because the reaction has a tendency to occur on its own. So first we can cover with this one, electrochemical cell, then we can move on to electrolytic cell. Okay. So can you give me some example of redox reactions which can happen on their own? Tell me any redox reaction which can happen on its own. Suppose if you put zinc, okay, zinc rod in copper sulfate solution. So what will you observe? Arshin, Dona, Anushka, tell me, what will you observe? If you put zinc rod in copper sulfate? Yeah. Any idea? Who's going to tell me, Arshin?
No idea, sir.
Yeah. Yeah. Okay. The displacement reaction is going to happen. Okay. Clear? So
Yes,
the
sir.
reaction is going to, yeah. So this is a spontaneous reaction. You don't have to push it again and again. It is going to happen on its own. Right, Dona? Is it clear?
Yes, sir.
So you can use this reaction, so it delta G is negative. Okay, means you can use this reaction to get electric current. Okay, but how you can use it? Tell me. Just by dipping it in. So first section which we are going to cover is electrochemical cell. Okay, so let me introduce electrochemical cell in detail. So suppose you take a solution of copper sulfate and you put a zinc rod in it. Okay, the reaction will happen. Yeah, Ryan, good evening.
Good evening, sir.
So we just started with electrochemistry. Okay, so this is a reaction which can happen. Okay, spontaneous reaction. You put a zinc rod in copper sulfate solution. The color of the solution will become lighter and lighter. Copper sulfate is blue. Okay, so it will become lighter after some time because the copper sulfate is reacting, and you will see the coppers from the copper sulfate is going to get deposited in as copper. Okay, is it clear? So I hope this is clear to you. But can you use it? can you use it to make cell? Can you use it to make the cell?
Yes, sir.
Yeah. So how will you make a cell out of it? Yeah. Tell me. So how will you make a cell out of it? This setup can give you the electrical energy. The present setup which I have shown over here. Yeah, Imad. Would you like to add anything?
No, sir.
Actually, you can't get the electricity. Okay. It is because the zinc and the copper are in direct contact with each other. Though the reaction can happen, but you will not be able to get the electric current. Right, Donna? Because
Yes, sir.
electrons are directly getting converted, directly leaving the zinc, and they are getting taken by the copper. So directly you are and the zinc and the copper ions are directly in touch with one another. So we can't harness that electric current. Okay. So you need to make a setup. Okay, to complete setup and setup that will let you harness the electrical energy and the flow of electrons for our use. Okay. So what you are going to do is, any idea, Rayan, Arshin, Anushka?
We are going to have two solutions, right? One of
Yeah,
Cl2 and one of C.
yeah. What you are going to do is, yeah, okay. So what you are going to do is you're going to separate the two components. Okay. You're going to separate the two components. Okay. And the zinc rod, you are going to put it in zinc sulfate solution. Okay. And copper rod, you are going to put it in copper sulfate solution. Okay. Is it clear? Okay. So you have separated zinc and copper solution. Now you can expect something. Okay, if the zinc want to give electrons to the copper sulfate is not directly in the same container. It is separated and it is put into another container. Are you getting? Imad, Rayan?
Yes, sir.
Yeah, now what you do, you will connect them with the help of wire. You will put a meter, okay, and voltmeter to check the voltage, EMF which you are going to get. Now what will happen? The zinc rod is being more electropositive. It is going to release electrons. And the electrons are going to flow from the zinc rod. Electrons. Okay. Initially, we were not getting those electrons because the zinc rod was directly dipped into copper sulfate solution. So that was, the reaction was happening, but we were not able to get anything out of it. The direction of current is actually taken as the direction opposite to the flow of electrons. Is it clear? So the direction of current is taken in this one, right? So this is how it will start working. And if we put a bulb or of appropriate voltage, okay, it will glow, right? Okay, clear? So this is what the electrochemical cell is. Okay. but we have just drawn it in a very crude way. You need to draw everything in detail, and there is a convention. Okay, so let me there is a way to represent this electrochemical cell, where to put whom. Okay, so what is actually happening is zinc is electropositive, that we know. So zinc will lose electron. Okay, is it clear? So zinc is getting oxidized. So oxidation is happening, and oxidation is the loss of electron. Okay, loss of electron, oxidation. Okay, and it is happening at the anode. This electrode where the oxidation is happening is anode. Okay, just you can think in a way that you have oxidation, there is a sound of O coming in, and there is anode. Okay, is it clear? So, and as per the convention, you put this anode on the left hand side. So on left hand side, you are going to put the substance which is more electropositive substance, which is going to lose electron by itself changing to ions. Okay, by losing electrons. Okay. So zinc is very electropositive. We know zinc is also used for electroplating of iron. That all of us know. So zinc is being taken as anode, right? Now, what will happen on the copper side? Can any one of you tell me quickly? What is going to happen on the copper side? Yeah, Donna, Arshan, tell me quickly. What is going to happen on the copper side? Ryan,
Reduction of
yeah, copper, actually the electrons are given by the zinc and they are flowing into the right compartment. Okay, so on the right hand side, let's see what is happening one by one. Okay, so right hand side, this is actually known as cathode. Okay, actually the electrons which are coming from the zinc rod side are taken by the copper ions, and the copper ions are getting reduced. Okay, this is the main reaction happening. So this is reduction. Okay, this is gain of electrons. And this is happening at cathode. It is called cathode because cations are getting attracted to it. And why the cations are getting attracted to it? Because electrons are coming in it. Okay, it is on the right hand side. Okay, right hand side reduction, and that is happening at the cathode. Okay, so you need to, though in the lab you can put them in any way you like. Okay, but while drawing the diagram of the cell, you need to put the cathode on the right hand side, anode. I'm talking about the electrochemical cell. Okay, Voltaic cell. Is it clear? Cathode on the right hand side and anode on the left hand side. Okay, so left anode oxidation, loss of electron. You can remember. So loss, oxidation, anode, there are a lot of O sound coming. Okay, loss, oxidation, anode, and that's going to be at the left, on the left hand side, and gain, reduction, cathode, that's going to come on the right hand side. Is it clear? So that's how this is the convention actually. Okay, it but in lab you can put it in any way. the cell is going to work. That's not the problem. But while you are drawing the cell, you need to draw it in this way. Okay, so after some time, you will see that the current will start flowing. You can measure some EMF or voltage, and you can measure the current through a meter. But after some time, the current stops. Okay, why the current stops flowing? With this setup, whichever I have given you. Anushka, Arshin, Donna, tell me why the current will stop with this setup, which I am showing you right now. Yeah.
So because the current is no more flowing through the wire. That's why.
Yeah, why it's no more flowing? Why it will stop? Yeah, there is something which is lacking in this diagram. Okay, and we need to understand the purpose of it. Yeah, Arshin, Donna, Rayan, Imad, would you like to add anything? What is lacking in this? Okay, and why the current will stop flowing? Okay,
Sir?
so what? Yeah,
So we use salt bridge, right? For the
yeah, we need to add salt bridge. Yeah, why?
So it will make sure that there is a continuous flow of current and the reaction is happening.
Yeah, but that is true. But actually, what is the role of the salt bridge, and how it makes the current, how it let the current flow continuously,
Sir,
and
it's
without salt bridge, yeah.
stabilization
Tell
of
me.
the solvent.
Yeah, you are very close to the answer. Let me give you the details. Actually, what is happening in the left hand side, there are zinc is electropositive. So the zinc atom present on the rod, they will leave the electrons and they will get into the solution and they will form ions. So zinc plus 2 ions concentration is increasing. Okay, right? And in a similar way, you can tell me what is happening on the cathode side with respect to ions. Yeah.
Sir,
Who's going to
C
say?
is
Hmm. Yeah.
Sir, copper is increasing in cathode.
No, not the copper. Actually, copper ions are accepting the electrons which were released by the zinc and they're getting deposited. Okay. Copper ion concentration is decreasing regularly because the copper ions are coming in and getting accepting electrons and they're getting deposited on the cathode. So actually you will observe that the cathode will gain weight after some time and the zinc rod will lose weight after some time. Okay, but how this is going to stop our reaction? Because the copper ions are getting diminished and the concentration of copper ion is decreasing. There were sulfate ion also. Okay, and they are actually left alone. Okay, so I would like to say the negative charge concentration, the negative charge is increasing. Right, initially what had happened initially, they were balanced. Okay, now what has happened? The copper is reduced, so and the copper concentration is decreasing. Okay, and this negative charge, because copper was positive initially, they were equal, positive negative were equal, and if you are keep on removing the positive, the negative charge concentration is increasing, and that's why the currents stop flowing after certain interval of time. Okay, so actually what you do, what's the remedy for this? Yeah, Dona and Arshan, would you like to add anything?
Introducing a salt bridge.
Yeah, salt bridge, right. So how a salt bridge is made, and what's the purpose of the salt bridge? Yeah,
Sir, I'm not completely sure the usage of salt, but I guess it helps in stabilizing the solvent.
yeah. So how a salt bridge is made, we can write that, and we need to also explain what's the purpose of the salt bridge. Okay, yeah, whatever you are saying is very true, correct, but we need to get into more detail how it is leading to the stabilization. Okay, so it's an inverted U-tube. You make a solution of agar-agar gel. Okay, you fill it in U-tube. When it is hot, actually it can flow, and when it cools, it just get accumulated in the U-tube. Okay, and you put some porous material at both the ends, okay, of the tube, filled with agar-agar gel, and not only agar-agar gel, it is mixed with a mixture of salts, okay, like potassium nitrate, ammonium nitrate, okay, potassium sulfate, are also mixed into the agar-agar solution. Okay, these salts, mixture of salts is put, and the ends of this tube, U-tube, is actually plugged with some porous material. Okay, that is glass wool or something like that. Okay, is it clear? So what is going to happen, right? It is going to solve our problem. Okay, how it is going to solve our problem? Okay, initially there was accumulation of, as you can see, initially there was some accumulation of zinc ions which was happening. Okay, so now what will happen is this, through this U-tube, through this end, both the end of the U-tube should remain dipped in the electrolyte solution. Okay, then only it will work. They should not remain in the air, otherwise the whole purpose of taking the U-tube will be defeated. Okay, so actually what is happening is this slowly the oppositely charged ions will come into the respective compartments, anode or cathode compartment, and they will maintain the electrical neutrality. Okay, so for example, on the anode side, left hand side, you are having accumulation of zinc. So slowly you will have the chloride ions. Okay, you have taken some KCl, or KCl also you can take. Okay, some chloride ions or some nitrate ions, NO3 minus ions, slowly percolating through that agar-agar gel into this. Okay, and they are going to neutralize the zinc. Similarly, on the right hand side, because the copper was getting neutralized, sulfate was getting remained alone. So in this side, actually, your positively charged ions like potassium, okay, or ammonium sulfate, if you would have taken ammonium, they are going to slowly percolate, okay, into the cathode compartment. So that's how the overall electrical neutrality will be maintained, and thus there will be no accumulation of unwanted charges happening in individual compartments. So the cell will again start working if you put the salt bridge. Is it clear? Imad, is
Yes,
it
sir,
clear or
yes.
not? Right, very good. So what's the purpose of the salt bridge? Yeah, tell me quickly, what's the purpose of the salt bridge? Arshin?
To neutralize the chemicals of the
Yeah, pardon?
to neutralize the chemicals.
Yeah, exactly. Very good. So it maintains the overall electrical neutrality of the cell. And prevents the accumulation of accumulation of charges in anode and cathode compartment. Okay, and it completes the circuit. Actually, suppose the negative charges, electrons are flowing from anode to cathode. Okay, electrons are flowing from anode to cathode. Okay, so the negative charge is flowing from anode to cathode. So there should be some oppositely charged ions which need to flow in the opposite direction, or to in appropriate direction, so that they can neutralize the negative charge. Okay, so it completes the circuit of the cell. Okay, but every time you may not be needing the salt bridge. What so have you seen a Danielson in your school laboratory in physics lab? Has anyone of you seen? Arshin, Dona, Anushka,
Yes, sir.
Sir, I
yeah,
think I have.
Danielson.
Could you just describe it?
Daniel cell is actually the same cell only, but they don't use two different compartments because it is very difficult. So what they do, they actually make a zinc or copper vessel, okay, copper vessel, and they put the zinc in porous container. So if there is a porous partition between the two compartments and that lets the charges flow, so then you may not need the salt bridge, okay. So that can also happen, but if someone asks you, then only you should say that, okay. Otherwise you should say how it is made, and what is the common way of making this, and what is the purpose. You need to just write 2 lines. I hope this is clear to all of you, right?
Yes, sir. Please.
Yeah, okay. So now the cell is going to work. Yeah, very good. So now the cell is going to work, but it is going to work as long as the reaction has not attained equilibrium. Okay. Now, because we have put the salt bridge, so we may think that the cell is going to keep on working. Okay. So it will start working again, but that doesn't mean that it will continue to work throughout its a lifespan. Okay, it is going to stop working, and when that moment arrives, okay, we use pencil cell, okay, and the pencil cell actually, you know that it stops working after certain time, okay. We need to replace the pencil cell or the batteries in our remote control and all electrical equipment which we use, okay. They stop working after certain time, because that is the point where they have attained the equilibrium, and they have all of their chemicals which were actually undergoing reaction and generating the current. Now they are depleted, so that's the point where the cell is going to stop working, and that is finally it will stop working, and now we need to replenish the chemicals again so that it can start working again. Okay, so now yeah, Anushka.
Sir, what do you mean by pencil cell?
Pencil cell, actually the cell which we use in I was just looking for that. I will be having, which we use in our home, okay, in various electrical equipment, in torch, or have you seen that? Okay, I'm having this pencil cell. Yeah, I was looking for it for you guys. In batteries which we use, okay. Let me show you just a second. So now, so it's stuck in my pen stand. Okay. Okay, this is the pencil set. Yeah.
Yes, sir.
Right. So how many volt does it produce? Can you tell me?
Sir, it's not that high, neither that low.
It's actually a 1.5 volt. Okay.
Yes, sir.
Right. So suppose if you want to put use 3 volts, so this is also an electrochemical cell. Okay, and there we don't need the salt bridge because there are two sections within one another, okay, and there is a porous separation, so that let the ions to move, okay, and that's how it maintains the electrical neutrality, okay. So because using 2 compartment and all that is going to be very cumbersome task, okay, and that will not be very handy. Now the next thing is, okay, next thing is here, there is a flow of current, all of us know, right? And this flow of current, right, when there is a flow of current, you might have studied in your physics. Can you tell me? Yeah, who's going to tell me when there is a flow of current? Yeah, Dona, Arshan, Hima, Rayan. When the current flows, when there is a what,
Sir, when there is
Anushka?
a movement in the electron.
Yeah, but when the electron move, I should ask that. When there is a, think of electrostatics, what you have studied in electrostatics and current electricity in physics, okay? Because when there is a potential difference, okay? Right?
Yes, sir.
When there is EMF, okay? So now the next question comes is how we are going to measure the voltage of the cell. Okay, that's the main thing now. How we are going to measure the EMF of the cell. Now we are interested. Okay, initially we started, we found that, okay, our cell is working and it is giving some electric current. Once we have that electric current, now we will be interested in the value of the voltage. Okay. So what voltage we are going to get? So the answer is very simple. Okay. The answer is very simple. So for example, just now I have shown you this pencil cell. Okay, and this generate 1.5 volts. Okay, this is the positive terminal, which is up, and this is the negative terminal. And there is a difference in voltage. Okay, a positive and negative. There is a difference of 1.5 volts between these two terminals, and that's the voltage which we get. Okay, so as a potential difference or voltage. Okay, so now in our question, our topic which we are doing is how much voltage we are going to get. That's the question. Okay, because that we need to know, because that's how we are going to able to predict how much voltage, how much current is going to flow, and how much work we are going to get out of this cell. Okay, and we can put some bulb. Okay, that bulb should have a voltage capacity of the one which is generated by the cell. Okay, it should not be out of the range, otherwise it will not work. Okay, so now everything comes to voltage or the EMF of the cell, of the potential difference. Okay, so any idea how we are going to measure it? What you people suggest? Arshin, Dona, Imad, Rayan, Anushka, tell me.
Not sure.
Yeah, okay. So the basic thing is, suppose if you want to find the potential difference generated by the cell, as the name indicate, potential difference. Okay. Okay, as the name indicate, potential difference. Okay, so suppose if someone can give us, okay, if someone can give us the potential of the left compartment, left electrode, and the potential of the cathode, and the potential of anode, then we can successfully predict. Is it clear? Are you getting?
Sir, I didn't understand.
Yeah, okay. Just a second. I think some connection problem. Okay, it's okay now. Yeah. So, yeah. So, suppose if someone asks you to someone asks you to calculate the potential. Okay. So, potential, how you are going to the potential or potential difference between the two compartments, anode and cathode. Okay. How you are going to do that? So it's very, so you will say it's very simple. Measure the electrode potential of anode and cathode. Measure the electrode potential of cathode. Measure the electrode potential of anode and take the difference. Is it clear? Are you getting it? Am I audible?
Yes.
Okay. So that's the, so how much voltage we are going to generate, how much potential difference we are going to generate out of these two compartments? The answer is very simple. Oh, you will say, okay, take the difference of the voltages of each electrode, and that's going to be the potential difference between the two electrodes, and that's the voltage or potential difference which we are going to get from this. Okay. So now my problem is EMF of a cell. I started EMF or voltage of this cell. Okay, that's what my question is, and the answer is measure the electrode potential of each electrode and take the difference. Take the difference of electrode potentials. So you can have the voltage of simply anode, that is simple one electrode. This is known, the setup is known as cell. Okay, but individual compartment is electrode. So if you have the electrode potential of anode, electrode potential of cathode, take the difference. Okay, and that will be the voltage, okay, which we are going to harness. Is it clear, Anushka?
Yes, sir, clear.
Right. So that's going to give us the potential difference between the two electrodes, right? Donna, Harshin, Syed, Imad, and Rayan. Clear. So, but now the question is how we are going to get the electrode potential of an individual electrode. That's what the question is. Okay. So electrode potential, how we are going to measure of individual electrode of, so let's say simply anode, simply cathode, how we are going to measure? Yeah. What's the way to do that? Anyone would like to add something? Imad, tell me. Rayan. So electrode potential of simply this. Electrode potential of only zinc electron, right? Clear? How we are going to measure it? If we have that, we can, and if we have the electrode potential of the copper compartment also. we can take the difference. But now question is how to measure electrode potential of individual electrode. So the problem which we are going to face is, without connecting it to someone else, you can't measure what's the voltage is. Because independently, if I give you the zinc electrode, and if I say, okay, tell me what's its electrode potential, you will say, okay, the current is not flowing because it's only zinc compartment. It's alone. How am I going to measure its electrode potential? Is it possible? The answer is no. Similarly, if I give you a copper electrode, and if I ask you, what's the electrode potential of this copper electrode? Will you be able to tell me? No. You will say no because it's not connected to anyone else. And if it is not connected to anyone else, there is no flow of current. And because there is no flow of current, you can't predict what's going to be the electrode potential. Okay, so there should be some means, some standard set, so that we can measure the electrode potential of each and every electrode with respect to that standard. Okay, and what that standard which is set by IUPAC is? Anyone would like to add something? Tell me quickly.
Not sure.
Okay, there is a standard which is chosen is, there is a standard which is chosen is the standard hydrogen electrode. Okay, is it clear? Right. So standard electrode which is chosen, which is assigned by IUPAC, that is standard hydrogen electrode. Okay, and we compare the electrode potential of each and every electrode by comparing it with standard hydrogen electrode, right?
Yes, sir.
So it's called She. So standard hydrogen electrode is a reference electrode. And this reference electrode can be connected to each one of them so that we can tell the electrode potential with respect to the standard electrode of each and every single electrode. Okay, And now we can take any two electrodes. We have this electrode potential, and when we connect them, we can take the difference, and that's going to be the EMF of the cell. Okay. Is that clear?
Yes, sir, clear.
Okay. So it's the standard electrode potential. So let me talk little bit about the electrode potential and little bit about the standard electrode potential. This standard hydrogen electrode and what it is, how it is made. Okay, and how it is used to calculate the electrode potential. Okay. So so types of electrode potential. Okay. So electrode potential is of two types. It is reduction potential and oxidation potential. Okay. Clear? So what do you mean by reduction potential? Tell me quickly. Yeah. Yeah, what do you mean by reduction potential? And what do you mean by oxidation potential for the same substance? Yeah, Imad, Donna, Priyan, Arshin, Anushka, tell me.
So oxidation potential was the tendency to lose electrons, right?
Yeah. So it's a measure of electron accepting tendency of the substance. Okay. So this is electrode potential of zinc. Which type of electrode potential? Standard or the reduction potential. Okay. I will use the term standard later on. So it's a reduction potential. And how it is denoted? So let me introduce the standard condition also. So these are the standard condition: 1 bar pressure, 298 Kelvin temperature, 1 mole concentration, and that these are the standard condition, and the electrode potential measured under the standard condition will be standard electrode potential. And this is standard reduction potential. And you write E naught which denotes standard conditions. Is it clear? The superscript not denotes standard condition. And how do you represent this reduction potential? In this way. Is it clear? So look, you
Yes,
need
sir.
to, here in this case, I have enlarged them and written it very large. But in the book, in the examination, it will be written very, very small. You need to check it very thoroughly. Okay, what it means, the zinc plus 2 is accepting electron and changing to zinc. So this is standard reduction potential. Okay. Similarly, this is it is a measure of electron accepting tendencies of a substance, zinc plus 2. Right? Is it clear to everyone?
Yes,
Right?
sir.
Okay.
Yes, sir.
So, what is oxidation potential? For the same substance, you can measure the oxidation potential also. So, oxidation potential is a measure of electron losing tendency. Okay, electron. So that is represented by this one. Okay. So you have to be very careful, because even if I also don't look very closely, I can get confused. In the same way, you people can also get confused. So this is reduction potential. It is represented by SRP value. And this is oxidation potential. Standard E naught represents standard. If you are taking zinc plus 2 concentration as 1 molar and pressure 1 bar 298 Kelvin. Okay, so this is SOP, standard oxidation potential, right?
Yes, sir.
Okay, so I hope if it is written, you can tell me. So, and for a same element, they have equal and opposite values. Let's say if it is minus X, so this is no other element, this is same, zinc. So if you are measuring the electron losing tendency, the electron gaining tendency will just be the reverse. Okay. So it's going to be plus X. Clear?
Yes,
What
sir.
is X? How you are going to measure it? Okay, how you are going to measure it? That's the that you need to check. Okay. So that is very important. Okay. So how you are going to measure it? You are going to measure it by connecting it to standard hydrogen electrode. Okay. Is it clear?
Yes, sir. Clear.
So what you do is, so what is standard hydrogen electrode? Let me tell you quickly. So this is a sealed platinum wire, okay? Because electrode need to have some metallic rod and need to have some wire. Okay, this is a sealed platinum rod kind of thing, and this is the platinum foil. Coated with platinum catalyst, powdered platinum, so that it can assist the redox reaction to occur. This is an hydrogen gas, as you can see from the top, is continuously bubbled through that glass column into the HCl solution, which is 1 molar. The gas pressure is 1 bar. Is it clear? The temperature is 298 because everything is under standard condition. Is it clear or not?
Yes, sir.
Okay, standard condition is standard hydrogen electrode, and this is the main electrode. Why? Because all the rest of the electrodes are connected to it to measure their individual electrode potential values. Okay. So how it is going to happen? Okay, so the two things can happen. Either the H plus, which is there in the HCl, can accept electrons. Okay, the H plus 1 molar HCl is equal to 1 molar H plus. Okay, either it can go and accept the electrons, right? And get converted to H2 gas, or the reverse may also happen. The H2 gas, which is coming from the top, bubbled from the top, can lose electrons, can lose two electrons. Okay. So both things can happen, and because this is standard electrode, so both the tendencies are taken as 0. Okay. Why 0? Because it is the reference electrode. Is it clear?
Yes, sir. Understood.
So this is the reduction potential value, and this is the oxidation potential value, as you can see over here. And that is equal to 0 volt. Okay. So if something is 0, and if you connect some other electrode to it, you assume it to be 0. Actually, it is how much you don't know. Okay. But there should be something which should be taken as 0. That act as a reference for all the rest. Is it clear?
Yes, sir.
So what happens is this is 0. So it's standard reduction potential as well as the oxidation potential. Both are 0. And all the rest of the electrodes are 1 by 1 compared to it, connected to it, and the voltage is measured. So because one of them is 0, so whatever the voltage which you are getting, that will be for that electrode which you have connected. Okay, and that's how you measure the electrode potential of each and every electrode. Okay, you need to write the explanation of this. Is it clear to all of you? So today, let me tell you what I discussed: the standard hydrogen electrode, how it is made, what's the purpose, what is electrode potential, why it can't be measured for an individual electrode. what are standard conditions, okay, what is reduction potential and oxidation potential, okay, and what are standard conditions, what is salt bridge, how it is made, and the basic definition, okay. These all these things are very important and very basic also. You need to have clear understanding and you need to express yourself very clearly in your examination, because they are asked every time in all sorts of, if the definition is not asked, you need to know to do the numerical questions, okay. That's very important. So I hope this is clear to you, okay. Right, so this is how it is happening. So you connect the zinc, okay. So zinc, you connect it to, I will draw a crude diagram, no need to draw the exact diagram, just to make you understand. This is zinc rod and this is zinc sulfate solution, 1 molar, okay. You put a salt bridge and or you just no need to put the salt bridge, just measure it immediately, instantly, because salt bridge is going to be required if you are going to run it for a long time. You're not going to run for the long time, just you need to measure what is the standard electrode potential of the zinc. That's it. Just for the moment you can do. And this is the standard hydrogen electrode H2 HCl, 1 molar, 298 Kelvin. Okay. So you can put the voltmeter here. Getting it? And voltmeter is going to give you the difference. Okay. So that is going to, the voltage is going to be called as EMF of a cell, that you can measure by reading of the voltmeter. This is the practical way of doing. You are not going to do that, but you need to know how it is done to understand it. So that is electrode potential of okay, you can read this value, right? And this is going to be 0.76 volt. I know, that's why I'm telling it. Okay. This is 0 volt. You have assumed it to be 0. Okay. So is it clear? That's how it is going to happen. And this is, but you don't have to worry about all this. You may be thinking that it is a very difficult task. Okay, yeah, it is a difficult task, but you don't have to do. You need to understand how it is done. That's it. So I hope everybody understood this.
Yes, sir, understood.
Arshin, Dona, Ryan.
Yes, sir. Understood.
Yes, sir.
Okay, yeah, this is how it is done. Okay, and actually, and there is one more thing which I would like to add. As I told you that the oxidation potential, the electrode potential of the individual electrode can be either reduction or oxidation potential for a single substance. It's going to have equal and opposite magnitudes. Okay, that we know, right? So the other thing is, so sometimes we are going to say reduction, sometimes we are going to say oxidation. Okay, then it is a problem for us, because suppose if we are comparing, there should be some homogeneity, okay, in whatever all of us. So there should be some homogeneity with respect to the temperature concentration. Okay, that we already did. Okay, right? 1 bar 298, and that's the standard condition. But there should be some homogeneity with respect to the electrode potential. So IUPAC has defined the standard electrode potential, the conditions, and as well as it has also defined which of the electrode potential should be considered as, though it is one and the same thing, you can work either in reduction or in oxidation, it is not going to change the things. But for homogeneity, IUPAC has taken the standard reduction potential as the standard electrode potential. Is it clear? As per IUPAC convention, you can write everybody can write it. As per IUPAC convention, the standard reduction potential, I can call it SRP, is taken as the standard electrode potential. Is it clear?
Yes, sir, clear.
Okay. And so you can work in both, that's not a problem. Okay, but for homogeneity, so that all of us can, suppose if I'm saying a standard electrode potential of zinc is minus 0.76 volt, that actually is minus 0.76. Okay, so now the question comes, you will say, oh, is it oxidizing or reducing? Okay, every time we have to ask this, unnecessary, it is going to create a confusion. So the IUPAC has eliminated this confusion by taking the standard reduction potential as a standard electrode potential. Okay, so you are going to take the reduction potential as its standard electrode potential. Okay, and each one is found by connecting with a standard hydrogen electrode whose electrode potential is taken as 0 because it is a reference electrode. Okay, and now we make a table. Okay, we list all these electrode potentials, and in the middle of the list you will find standard hydrogen electrode which has a value 0 volt. Okay, so these lists are given in each and every book. Okay, and that list is known as electrochemical series. Okay, it is a list of electrode potentials of different electrodes when compared individually by the reference electrode which is standard hydrogen electrode. So it makes our life very easy. These values will be given to you in the question. So 2 electrode potentials will be given, standard electrode potentials. You, and suppose if I ask you, make a cell out of it and tell me what's going to be the EMF which you are going to obtain. Okay, so the 2 values which are given to you, you are going to take the difference. Okay, and you are going to tell me what is the maximum voltage which I can get if I connect these 2 electrodes. Is it clear? Okay, so now the next thing is which we are going to discuss is, so I hope how we are getting towards electrochemical series. Okay, is it clear?
Yes, sir.
Electrochemical series. Okay, so it is a list. It is nothing but a very fancy name, but it is simply the list of all the electrode potentials, reduction potentials. Why reduction potentials? Because IUPAC has given, IUPAC has taken the reduction potential as standard electrode potentials. Okay, so I hope this is clear to you. So electrochemical series and the questions related to, and we will be able to calculate the EMF. We are going to discuss it on the next time. By the meantime, you can go through your NCERT and I hope you will understand each and everything. Just go through it, okay? And let me know if there is any doubt in the next class. So let me end today's class, okay? And do revise your notes from NCERT, okay? So bye everyone. Good night. Take care. Anushka, Arshin, Dona, Imad, and Rehan. Bye all, everybody.